In this class, we will see one more aspect in the simplex table. We consider a specific linear programming problem, solve it using the simplex algorithm and the table, and then when we find something specific happening, we will try to explain what happens to the linear programming problem. So, let us consider this linear programming problem with two variables and two constraints. It is a maximization problem with 10x1 plus 9x2 familiar objective function, but the constraints are different. We have x1 plus x2 less than or equal to 5 and 4x1 greater than or equal to 24 with x1 x2 greater than or equal to 0. So, as usual we convert these inequalities to equations by adding slack variables. Now, x1 plus x2 less than or equal to 5 is converted to an equation by adding a positive slack variable x3. So, plus x3 equal to 5, x3 greater than or equal to 0. Now, 4x1 greater than or equal to 24 will involve a negative slack. So, 4x1 minus x4 is equal to 24 and x1, x2, x3, x4 greater than or equal to 0. So, as we have seen before, this greater than or equal to constraint has resulted in a negative slack, variable, and this negative slack variable cannot be a starting variable for the simplex algorithm. Therefore, we introduce the artificial variable here with a1. So, a1 is the artificial variable. So, x1, x2, x3, x4 and a1 greater than or equal to 0. The two slack variables x3 and x4, one is a positive slack and the other is a negative slack, they do not contribute to the objective function. The a1 variable to the minimization problem would have contributed a big M, and for the maximization problem it contributes a minus big M. The motivation again, as we saw earlier, is that now we have written a new problem by introducing the artificial variable. If this problem is going to be solved from which we are going to get the solution to the original problem, then we have to make sure that the a1 does not come in the solution of this problem. The way by which we implement it is, for a maximization problem, if the coefficient is a very small number, remember m is a large positive number tending to infinity, minus m is negative of m, therefore it is a large number but with a negative sign, and therefore is not expected to appear in the solution because its contribution is very small. In fact, its contribution is negative. So, it is not expected to come into the solution of a maximization. So, this is the new problem that we will solve because of the greater than or equal to constraint, which necessitated in a negative slack and necessitated in an artificial variable. There is only one artificial variable, there are no two artificial variables, there is only one, and that has a minus m. So, we now set up the simplex table to solve this. So, there are 5 variables, the two decision variables x1, x2, the two slack variables x3, x4 and the artificial variable a1 that we have here. So, we write the objective function values 10, 9, 0, 0 and minus m that comes. Please note that this minus m is coming because of the artificial variable and the maximization function. So, there is a minus m in the objective here. The equations are x1 plus x2 plus x3 plus 0 x4 plus 0 a1 equal to 5. So, we write x1 plus x2 plus x3 plus 0 x4 plus 0 a1 is equal to 5. Second equation is 4x1 minus x4 plus a1. So, 4x1 plus 0 x2 plus 0 x3 minus x4 plus a1. So, 4x1 plus 0 x2 plus 0 x3 minus x4 plus a1 equals 24. So, we write the two basic variables. Now, we realize that we can start the simplex with x3 and a1. Now, x3 and a1 put together actually have the identity matrix. In this particular example, x2 and a1 also can give us the identity matrix, but we start with x3 and a1 to be consistent that if there is a slack variable, we start with the slack variable. So, x3 and a1 are the two variables with which we start the solution. Now, the objective function coefficient of these two variables are x3 has a 0 contribution, a1 has a minus m contribution. So, 0 and minus m. Now, we need to check whether this solution is optimal or whether there is a variable that can enter the solution with a positive Cj minus Zj. So, we calculate the Cj minus Zj values. Now, for variable x1 it is 0 into 1 minus m into 4, therefore, it is minus 4m. So, 10 minus 4m is 4m plus 10 or 10 plus 4m, which is shown here, 10 plus 4m. For the variable x2 it is 0 into 1 minus m into 0 is 0. So, 9 minus 0 is 9. So, this value is 0 into 1 minus m into 0, 0. So, 9 minus 0 is 9. For variable x3, the Zj value is 0 into 1 minus m into 0, 0. So, 0 minus 0 will be 0. For variable x4, it is 0 into 0 plus minus m into minus 1 is plus m. So, 0 minus m is minus m. And for the variable a1, it is 0 into 0 minus m into 1 is minus m minus m minus minus m will be 0. Once again, you can observe that the two basic variables x3 and a1 will have Cj minus Zj values as 0. They will have Cj minus Zj values as 0. The value of the objective function will be 0 into 5 plus minus m into 24, but since an artificial variable is in the solution, we do not write the value of the objective function. Instead, we keep this value as dash. So, we now have to check whether there is a variable that can enter the solution. So, x2 can enter the solution with 9, x1 can enter the solution with 4m plus 10. Now, m is large and positive, therefore, 4m plus 10 is bigger than 9. Therefore, the variable x1 will enter the solution because it has the larger value of Cj minus Zj between the two variables. Once again, this is 9, this is 4m plus 10, m is large and positive and tends to infinity. Therefore, 4m plus 10 is bigger than 9. So, variable x1 enters the solution. Now, x1 has to replace either x3 or a1. So, we find the ratios. 5 divided by 1 is 5 and 24 divided by 4 is 6. The smaller one is 5. Now, x1 will come into the solution and replace x3, and the artificial variable stays in the solution. Now, let us look at the next iteration. So, I have captured the first iteration in this table, where variable x1 entered the solution with 4m plus 10 and the variable x3 left the solution. Now, this is your pivot element. Now, the new basic variables are x1 replaces x3 and a1 remains. So, we will have x1 and a1 in the solution. x1 is replacing x3, so x1 comes here, a1 remains. The value of the objective function coefficients are 10, and minus m. x1 has 10, a1 has minus m. Now, this is the pivot element. So, divide every element of the pivot row by the pivot element. Since the pivot element happens to be 1, the same values will repeat. So, 1 by 1 is 1, again 1 by 1 is 1, again 1 by 1 is 1, 0 divided by 1 is 0, 0 divided by 1 is 0, and 5 divided by 1 is 5. Now, variable x1 is in the solution with a 1. So, I need to get a 0 in this position, I need to get a 0 in this position, as well as retain a 1 in this position, retain a 1 corresponding to a1. We need to do that. Now, we go back and visit the corresponding position, which is 4. So, 4 I need a 0, 4 minus 4 times 1 is 0. So, every element here I take this and then I multiply this one by 4 and subtract. So, I will have 4 minus 4 times 1 is 0, 0 minus 4 into 1 is minus 4, 0 minus 4 into 1 is minus 4, minus 1 plus 0 into 4 is minus 1, minus 1 plus 0 into 4 is minus 1, plus 1 minus 0 into 4 is plus 1, and 24 minus 5 into 4, 20 is plus 4. Now, this is the solution, x1 equal to 5, a1 is equal to 4. Now, we want to check whether this solution is the best solution. To do that, we have to find out whether there is a variable that can first come into the solution, for which we have to find out the values of Cj minus Zj. So, we write Cj minus Zj and find out the values. 10 into 1 minus m into 0 is 10, 10 minus 10 will be 0. 10 into 1 is 10, minus m into minus 4 is 4m. So, 9 minus 10 minus 4m is minus 4m minus 1, minus 4m minus 1. For variable x3, 10 into 1 is 10, minus m into minus 4 is 4m. So, this part is 4m plus 10, 0 minus 4m plus 10 is minus 4m minus 10, written as minus 10 minus 4m. For variable x4, it is 10 into 0, 0, minus m into minus 1 is plus m. So, 0 minus plus m is minus m. And for variable a1, 10 into 0 is 0, minus m into 1 is minus m. So, this minus m minus minus m will be 0. Now, the value of the objective function is 10 into 5, 50 plus minus m into 4. So, 50 minus 4m, but we do not write it because the artificial variable is in the solution. Therefore, we write only a dash coming here. Now, we want to check whether this solution is optimum. We have reached the optimum solution, or is there a variable with a positive value of Cj minus Zj that can come into the solution. Now, variable x1 and a1 are basic, so we do not consider them. We consider x2, x3 and x4. Now, we realize that this value of minus 1 minus 4m is negative because m is large and positive. So, minus 4m is negative. So, minus 4m minus 1 is negative. Similarly, minus 10 minus 4m is also negative because m is large and positive. So, minus 4m minus 10 is also negative, minus m is also negative. Therefore, there is no entering variable. The algorithm terminates normally without any difficulty. The algorithm terminates, and we could say that x1 equal to 5, a1 equal to 4 is the solution. But when we started with the simplex algorithm, when we when we started with the simplex algorithm for this particular problem, we wrote the artificial variable here because this constraint had a greater than or equal to. We wrote an artificial variable here and this artificial variable came into the solution. Now, when we wrote this artificial variable was introduced only for the sake of starting the simplex algorithm, and this was not part of the original problem. So, we said we do not want this artificial variable to be in the solution, and the way we handled it is by giving a large positive value m and by putting a minus m in the maximization objective, so that a large negative contribution prevents this variable from being in the solution. So, we thought that by putting a large negative contribution here, big M is large and positive, so minus m is a large negative. So, by putting a large negative contribution, we will prevent this A1 from coming into the solution, so that if this problem has a solution, now this problem will show the same solution and this problem's solution will not involve A1. So, we started with that principle, but we observed that when simplex terminated, A1 is actually in the solution and we do not want it. So, we are, in spite of us putting a big M and putting a large negative contribution, thinking that the variable A1 will not be in the solution, we now observe that the variable A1 is in the solution. So, the variable A1 is in the solution. So, once again revisiting this, we said that if this has a solution, then by putting a large negative value, we will prevent A1 from coming into this solution, and solving this problem will give the same solution to that of this problem. But now, in spite of us putting a negative contribution, A1 is in the solution, it means that the original problem does not have a solution at all. Now, this is called infeasibility. The original problem does not have a solution. So, infeasibility is indicated by simplex terminating normally, but after simplex terminates, there is an artificial variable in the solution with a strictly positive value. If there is an artificial variable with a strictly positive value when simplex terminates, and there is an artificial variable in the solution with strictly positive value, we say that it is infeasible. Now, we will also note this value is 4, and then we will also see how the graphical method looks at the same problem. So, we now go back to the optimum is reached, but artificial variable is in the solution, indicates infeasibility of the linear programming problem. Now, let us go to the graphical method. We have the same problem, we draw the axis with 0 and 0. Now, this is for variable x1 and this is for variable x2. For variable x2. We now draw the two lines, x1 plus x2 equal to 5 is drawn here with points 5 0 and 0 5. This is the point 0 5. Now, origin 0 0 satisfies the inequality x1 plus x2 equal to 5. So, this is the feasible region, the triangle that we have shown in a different color is the feasible region to this problem. Every point on this, including these points, is the feasible region for the first constraint. Now, we draw the second constraint, for x1 equal to 24 or x1 equal to 6. Now x1 equal to 6 is a line parallel to the x2 axis or the y axis passing through the point x1 equal to 6, and this point is 6 comma 0. So, this point will be 6 comma 0. So, this is 6 comma 0 and this is the line for x1 equal to 24. Now, we have to find out that region which satisfies the inequality. So, the origin is here 0 0 is actually less than 24, therefore, the other region is the region that satisfies this inequality. This is the other region is the region that satisfies the inequality. So, we show the other region now this way. Now, we realize that the other region is the region that satisfies the inequality. Now, if we look at the feasible region associated with the two constraints, we have one constraint where this portion is the feasible region. For one constraint, we have this portion is the feasible region, and for the other constraint, the feasible region is somewhere here. So, we realize that this feasible region, there is no actual region which satisfies both these constraints. When we have two constraints where there is no set of point and there is no point satisfying this together, then we say that the problem is infeasible. Now, this infeasibility is indicated by the simplex algorithm with the presence of an artificial variable in the solution. Now, that artificial variable had a value a1 is equal to 4. Now, that a1 was actually introduced in this constraint, in the second constraint 4x1 greater than or equal to 24. So, this constraint became 4x1 minus x4 plus a1 equal to 24. So, if a1 is equal to 4, we would get 4x1 greater than or equal to 20, which is x1 greater than or equal to 5, and if we had plotted that, now this line 4x1 equal to 24 would have become 4x1 equal to 20, and it would have come somewhere here, showing that the point 5 comma 0 is the optimum solution. But because we had 24, the LP solution was suggesting that a1 should be equal to 4, so that 4x1 becomes greater than or equal to 20 and we can get a solution. But right now there is no solution because a1 is equal to 4. So, the presence of the artificial variable, in the solution not only indicates infeasibility, but also gives us a way to understand the amount of infeasibility or the extent of infeasibility to the linear for the given linear programming problem. So, at the end we say that there is no region that satisfies both the constraints. The given linear programming problem is infeasible. So, in this class we have seen infeasibility. In the earlier class we saw unboundedness, and we saw how simplex handles both infeasibility and unboundedness. So, there are essentially three things to a linear programming problem. The linear programming problem, any problem, either has an optimum or is unbounded or is infeasible. Only one out of the three can actually happen for a given linear programming problem. We have right now seen all the three instances. There are still a few more things that can happen when we actually do the simplex iteration. Now, those things we will study through examples and exercises as we move along in this course. In the next module, we will move forward to study another interesting aspect of linear programming, which is called duality.